All right, welcome to our session. So my name is Ryan Ward. I'm currently working in New Zealand, and Greg asked me to introduce him, and I'm really happy to be able to introduce Greg today. Greg started his undergraduate career at Reed College, working with Alan Nuringer, who all of you should know, if not personally, certainly through his contributions to the field. And after that, he went to work at Columbia University with Peter Balsam for a PhD, where he also rubbed elbows with Randy Gallistel, and then did a postdoc in Herb Terrace's lab, where he ended up being for, I guess, the better part of the last 10 years or so, really studying quantitative modeling of emerging preferences, processes that have traditionally been given sort of like a higher cognitive explanation, just really trying to dig into what's going on there. And he's now returned back to Reed, where he started as a faculty member, to sort of mentor the next generation of students. And I don't want to take too much of Greg's time, because I think it would be well worth what he has to say. But just, I met Greg as a postdoc in Peter Balsam's lab. He was doing his PhD there. And one of the things that I think summarizes Greg's approach to science was, I can't remember when it was, but I approached him at some point because I had heard that he was like a whiz with statistics and, quantitative analysis and stuff. And I said, hey, I got this data set, can you help me, make sense of it or whatever? And he asked me a question that I hadn't been asked before, but I think it typifies his approach to his science. And he said, well, the first thing, how are the data distributed? And I said, I thought to myself, well, I don't know, they're just data, I have them in an Excel sheet, whatever. But I think for me, and interacting with Greg over the years, he really, he lets the data drive what he's doing, right? I think a lot of times in science, we get caught up in phenomenon, and we gather data, and then we try to sort of fit a model or make our data fit the model, right? But Greg's approach, I've worked with him over the years now, we collaborate on a number of things. He lets the data drive the models, right? He doesn't look at aberrations of data as a problem that needs to be sorted. He says, what do the data look like? That's telling us something fundamental about the underlying process. And I think that that's an uncommon strategy to the kind of science that we do. The other thing that's uncommon about Greg is his ability to distill incredibly complex topics to their essence in a way that is accessible to people from a broad variety of backgrounds. And so I think we'll be treated to that today with his talk. So it's my pleasure to introduce and welcome Greg Jensen.
All right, just get started here. Okay, so no pressure, obviously. Let's just distill information theory down into a basic introduction. So what I want to start with today is I want to sort of start with a metaphor that I'm borrowing from Richard McElrath, because it's often said that mathematics is the language of nature. This is an old adage, and I don't think that this is actually usually true. But I do think that mathematics is a language that is very well suited to natural metaphors. And so this analogy that I think is a useful sort of way to start thinking about what I'll be talking about today is this idea of the small world of the model. We have a model, we can put data into the model gives us predictions. Within that world, all the rules are defined. Everything is explicit, it's specified. And anything that is not in the model, in a sense, doesn't exist in the small world. And therefore, in the small world, it's possible for outcomes to have a defined probability, and any series of outcomes can be known in advance. And a probability can be calculated for them, you can make predictions. Of course, we don't live in the small world, right? We live in the messy reality of the large world where nothing is known with any actual certainty. Absolute certainty is unavailable to us, which is, on the other hand, why science is interesting. So with this sort of frame, let's start talking about information theory. So information theory can be characterized as a flexible framework that relates information storage and communication as problems to the laws of probability as tools. And our first goal today is going to be to measure how complicated a particular small world is, right? We're not going to measure how complicated the real world is. We're going to take some little pocket mathematical universe where the rules are clear, and we're going to measure its entropy. More complicated models are harder to study scientifically. They have more moving parts, they have more interactions, and they should therefore also be harder for subjects to learn in some kind of an associative setting if there's a complex series of relationships that is going to maximize reinforcement. It's also harder for the little folk scientists that are our research subjects to deduce those relationships. The second goal for today is going to be to evaluate whether the data we have is consistent with some model, because after all, we heard it during the meetings at SQAB, we don't live in the small world, all models are wrong. And famously, some models are nevertheless useful, but we don't have access to the perfect model that captures every single idiosyncrasy of every single lever press. We generally deal with the broad strokes, right? Some models do a worse job at predicting data than others. Some models give us less insight into the underlying phenomena of the world. And so we can measure this discrepancy between data and models using the information theoretic quantity called surprising. So I want to spend some time really motivating this as a measure of model discrepancy. Now this is a quote attributed to John von Neumann when he had conversations with Claude Shannon about why he should call information theory's main measure entropy. And that is that no one knows what entropy really is, and therefore no one can tell you that what you are doing is in fact incorrect, right? No one can tell you that you've defined entropy incorrectly because no one knows what it is. Everyone thinks they know what information is, so they're going to fight you on the definition. This was John von Neumann's salesman side saying, hey, here's how you control the conversation. So at its most basic level, entropy is a measure of how long a description is needed to describe the particular state of the small world. Here's some scenario in your small world. How long a message would you need to send to describe that situation completely? Equivalently, it is also how hard it is to predict a future state. So if you know what the current state of the world is, how long a message will the future send to you? How surprised are you going to be? How much are you going to learn by the next observation you receive? And this entropy formula, that, in its most basic form, this is often called Shannon entropy, presented as a sum, can be read in the following sort of plain English form. For every state little x that is possible within some small world big X, multiply its probability by its log probability, take the sum of all those, and flip the sign. So common events are going to have a large probability, but their log probability is going to be close to 0, right? Since probability is bounded between 0 and 1, any probability close to 1 is going to have a log value that's going to be close to 0. Rare events are going to have a small probability, but a correspondingly large log probability because that's going to tend towards negative infinity as the probability gets closer and closer to 0. And then we flip the sign because otherwise all these would be negative and we don't need that, we don't need to waste the ink, right? So these two effects balance out in the sum. And it wouldn't be a conversation about probability if I didn't talk about coins. Look, it's in my contract, I just have to talk about coins. So the very simple case of flipping a coin lets us visualize this. And let's imagine, just for the sake of argument, that there are coins that aren't fair. Here's what the range of the entropies would be for those varying degrees of fairness. In the world where you flip a coin and it only comes up heads, maybe because it's got heads on both sides, entropy is 0. You don't learn anything by flipping the coin. You're not surprised by the outcome. and correspondingly, a coin that only comes up tails teaches you nothing. You don't have, like, you can effortlessly prognosticate its outcome. However, because the log of a half is -1, and 2 times a half of the log of -half adds up to being 1, you can say meaningfully that a fair coin corresponds to 1 bit of information. I'm using bits here because I happen to be using log base 2. We'll relax that requirement for the moment, but for the time being, we can assume I'm talking in bits. Literally, how many 1s and 0s. And a coin flip that is fair corresponds to about 1 bit of information, because you don't know if it's going to be a 1 or a 0. Therefore, the entropy of a coin is highest when both are equal. Right? Right? Or maybe not? What if you called edge? Let me introduce you to the 2016 SMIC. This is a coin that was minted about 6 years ago. It's 20 millimeters across and it's 9 millimeters thick. It's a solid ounce of silver, and if you flip this coin, your chances of getting edge are non-zero. Even, I mean, like, probably it's not going to be a third, but it's going to be higher, right? So rare cases can exist, and even in a normal coin, right, a nickel, it has the flat edge, right? It's not a beveled edge. It could land on its edge. It's a possibility. So how do we deal with these cases? It would be very hard to flip a coin, sight unseen, and call that it was going to land on its edge, right? If someone flipped a coin and called edge, you're officially in a high magic zone. The laws of physics are out the window, right? That's a problem. Since edge is a very rare outcome, it makes almost no contribution to the total entropy. So we have to make sense of this, and to do that, we're going to use this idea of surprising. The common notation for this, which admittedly is going to be a little confusing down the line, is capital I sub big X of X is the surprisal of an event, small x. So how surprising is the next coin flip? That's what we're trying to measure. And the surprisal is measured by the negative log probability of that event, or correspondingly, the log of 1 over that probability. So how surprising is it when the coin comes up edge? Well, just to make the math work out very nice and cleanly, let's suppose that there's a 1 in 4,096 chance of getting an edge when you flip a coin. In that case, the surprisal for getting that outcome would be log base 2 of 4096, which is 12 bits. So even though the entropy for flipping a coin feels like it should be about 1 on average, there's 12 bits worth of surprise when it hits edge, right? That's a very surprising result. But when you look at the average of how often that's expected to happen, if you're multiplying that log probability by the probability of 1 over 4096, then guess what? You're actually only contributing 0.003 bits to the average running entropy. And this gives us a new way to think about what entropy is, what Shannon is talking about when Shannon uses this idea of entropy. Shannon is the average surprisal that we expect to experience. So we can take our previous formula and rewrite it as follows. We can think about this as just how often the event tends to occur. In a long string, that's going to be the proportion of observed events. And this is the surprisal. It's just log of 1 over the probability. That way we get to get rid of that pesky minus sign. In other words, the entropy of a particular random process is the average surprisal experienced per event. That's all it is. In some long stream of events, what's the average degree to which each new event surprises you? You might still get edge sometimes, but not very often. And as a result, a fair coin is still going to have about 1 bit's worth of uncertainty, even if that edge case is floating around in there as a rare probability. Surprising events that are rare contribute little to that average, but are very surprising on the specific cases where they occur. In other words, we can still talk about a fair coin that we pulled out of our pocket having about 1 bit's worth of uncertainty, even though edge is a third option that we may have neglected to include in the equation. And many super rare events end up having this kind of quality in our statistical models. Now, more broadly, we can view this normative amount of surprise as the amount we expect to experience per event when sampled from X, right? How surprised should we be per unit time. Now with this in mind, I'd like to walk through a sort of a concrete scenario here, a sort of a simple associative scenario. Imagine that there's a rat in a long chamber, and at one end of the chamber, there's a tray where food pellets are being dropped occasionally. Now numerically, we might summarize this with one of these classic sort of schedule diagrams, but we're gonna need to get specific. So if you actually measure out the proportion of the line where I have drawn one of the little rectangles to indicate the availability of a pellet, pellets are available just shy of 8% of the time, which means that 92.1% of the time, food's not available. So we can calculate the entropy of when food is available by just crunching the numbers, right? Probability times log of times the surprisal, probability times the surprisal, and it adds up to about 0.398 bits. Suppose simultaneously and independently that the chamber has a red light that's on about 10% of the time. We can characterize that in terms of one of these diagrams, and we can say that if we average over time, there's going to be a 10% probability of the light being on. That means there's going to be a 90% probability of the light being off, and we can figure out that that, in turn, has an uncertainty of 0.469 bits, which, right off the bat, it's a little harder to know when the light's going to be on if your eyes closed than to know whether there's a pellet in the tray before you check the tray. These measures are how surprising each of them are, provided we don't know the other stimulus, because I haven't told you anything about how these two are associated yet. If these two are independent, this is how hard each of them is to predict. So what if they coincide to some degree? So let's combine these onto a common timeline, and here it becomes immediately obvious to the eye that these are probably not statistically independent events. But again, we have to be precise. The odds of the food being available when the red light is on is 7%. The odds of the food not being available when the red light is on is a little bit lower. It's about 3%. And there is a very slim rate at which there's food available with no red light. You'll notice that I've offset one of those ticks a little bit. Maybe there was a technical malfunction, right? Maybe the solenoid needed to jump another time to release a pellet or something. And then finally, the remainder is that most of the time, there's no food and no light. If you just needed to predict what the state of the box is, you would say probably both of them are off, most of the time. If we put both of these together, if we treat all of these independent events, these four different combinations, we can calculate the joint entropy across the food and the light. Now this looks like a hairier equation, but it's really just the same equation as before. It's just the probability for each joint event times its log probability with the minus at the front, which is just another way of dealing with the reciprocal and surprisal. And so in this scenario, the overall ability to predict which of the four states we are in is about 0.63 bits of information. So still easier to predict than a coin flip, right? Most of the time you just say, they're both probably off. Now, how do we go from here to beginning to think about associative processes? What if we try to predict one outcome based on the other? What if I'm on one end of the chamber and I see that the red light is on and I want to know whether it's worth my time to go check whether there's food? I'm ignoring for the moment that yes, when the solenoid flips, the rat can hear the solenoid. Like, we're keeping this is in the small world, right? In the small world, we don't have to deal with the idiosyncrasies of the machinery. We can keep things very clean. So to see this, what we're going to need is a related quantity called the conditional entropy. So far, we've just been taking products and sums with some logs mixed in. Now we're just going to take a difference of two things we've already calculated. So the conditional entropy of food, given that the red light is on, is going to be the joint entropy minus just the entropy associated with the light. Just simple subtraction. And correspondingly, we could, if we wanted, so for example, if the rat couldn't see, the rat could predict when the light was on based on the availability of the food. It could go either way. So if we actually work through the math, given that I mentioned the numbers before, our joint probability was 0.63, our probability for just the red light alone was 0.469, which means that our ability to predict the food has been reduced to only 0.161 bits of information. Now, I've just been reading a bunch of numerals to you. It's not particularly compelling, so let me make this concrete. We've cut our uncertainty in half. We had a certain level of uncertainty, 0.398, before we knew that the food and the light had any association. But once we are pinning our predictions on the existence of the light, once we know the state of the light, our uncertainty has been cut in half. We know the state of the world with more confidence than we did before. We're less likely to be surprised than we were before. And we could do this same calculation to predict the light in terms of the food, right? It's just a subtraction. Now, there's one final little piece of arithmetic that we can do to really get something powerful. And that is to calculate what's called the mutual information. Now, good news, there's 3 different ways to calculate this using the pieces we already have. Each of these equations in red is equivalent, right? You just like do the arithmetic, and these are all the same thing. You can either take the entropy for the food and subtract away the conditional entropy, or you can take the entropy for the light and subtract away the conditional entropy, or take the joint entropy and get rid of both of the conditionals. Any way you cut it, you're going to get this thing called mutual information. Now again, I'm showing you too many equations, so what I want to do instead is to visualize the entropy. Here is the entropy as a literal block of uncertainty. I want you to imagine every pixel that is on the screen here is a unit of entropy, right? The physical size of this box is meant to directly correspond to the numbers we've been looking at. And here is how the arithmetic breaks that down into those 3 parts that we can now calculate. The blue is going to be the conditional entropy. It's how much we don't know about the red light given the food. The burgundy is going to be the conditional entropy of food conditioned on the light. It's how much we don't know about the food once we know about the light. And everything else, that middle area, which confusingly is I of F and R, I said the surprising notation was going to be confusing, I apologize. It's information, it's the letter I. I can't change the notation. But this overlap is the degree of information that is shared between the 2 stimuli. The bigger the mutual information is, the more knowing one outcome helps you predict the other outcome. Now let's really see what this implies by working through a second example. So here's a different scenario. Same chamber, maybe we rigged something up on the other end of the chamber. Now there's a dipper at the other end that raises to sometimes make condensed milk available. Again, we can diagram this in terms of one of our classic schedule diagrams, but we need to get specific, so we'll calculate that the milk has nearly the same probability as the food pellets dropping, which means the complement is also nearly equivalent. And we can calculate that gives us nearly the same uncertainty for predicting milk overall, free of any other stimuli. But the green light is on at random 25% of the time. So it takes up more of the timeline. And consequently, it's going to have a higher probability of being on, a lower probability of being off, and its entropy is going to be quite a bit bigger. Remember that the entropy for the red light was just shy of 5, this is just shy of 0.5, this is a little above 0.8. So in general, it's harder to know when the green light is on, or when to anticipate when the green light's going to be on, than when the red light's going to be on. Because here, it's closer to 50-50, right? It's closer to a coin flip. Whereas in the case of the red light was almost always off. But is it actually easier to predict when the milk is going to be on, when the milk is going to be available relative to the green light, than it was to predict the food pellets relative to the red light? So let's go very quickly through the same math we did before. We put both on the same timeline. At a glance, it doesn't look nearly as good, right? But again, let's get specific. So we've got our 4 actual joint probabilities. They appear together a little more than 6% of the time. Milk fails to appear almost 19% of the time that the green light is on. So the green light is actually on a larger share of the time without milk than with milk. Milk also appears about 1.5% of the time without the green light, and then the remainder is all of that other dead time. So if you had to make a prediction, you would still say, sight unseen, I think they're probably both off right now. But there's more uncertainty here. And when we calculate the joint entropy, the various entropy measures, predicting milk on its own, as we mentioned, the conditional milk is still above 0.3. If we wanted to predict the light, the conditional light's only a little bit smaller, it's about 0.7. And this brings us to a joint entropy of 1.12, but mutual information of merely 0.8. So this is a harder situation to predict than a coin flip. And we learn very little about the milk from the light. Now again, throwing a lot of equations at you, I'm just flying through some arithmetic. Let's visualize it. Here is the block of uncertainty associated with milk and green light. These are the same units as the previous block. You'll notice it's wider on the screen. And this block can be broken down again into two parts. And you'll notice that the mutual information here is decidedly smaller. I had to make the font small to actually fit it horizontally in the space. And since I've used the same measure, the same scale for these informational units, we can actually bring back the block from the first scenario, which is right here. Again, the size of the block as I've drawn it here precisely corresponds to the numbers I showed you before. And remember that I told you that milk and the milk dipper and the food pellets by themselves, absent any stimuli, had the same level of uncertainty. You'll notice that those blocks are both the same size. But the mutual information is much larger for the relationship between the food and the red light than it is between the milk and the green light. You are going to learn almost 3 times as much per observed state of the world because the mutual information is nearly 3 times as big in that schedule. Does that make sense? I'm seeing some nods. I love to see those nods. So what does this tell us about the idea of trying to evaluate our schedules from a normative perspective? Here's the process. Here's sort of a simple recipe for how to proceed. 1, list each possible combination of schedule states, right? Food available or not available, light on or off, buzzer on or off, whatever stimuli you would like to use, just enumerate what those possibilities are. Count how often each state and each combination of states exists. Once you have those numbers, just both the base rates for the states and their joint appearances, you can just calculate the information for x, y, and the joint entropy from those proportions. You can then calculate the conditional entropies and the mutual information from those values. And the prediction is, the normative prediction that is not probably going to be true, but that is the starting point, is that the time subjects need to associate x and y is inversely proportional to the mutual information. Now, why do I say this? The way that we can conceive of this, and again, this is entirely normative, it depends on the animals being able to perceive the events, being able to understand the environment. This is a best case scenario. We can conceive of mutual information as the evidence gained about the association of the variables each time we observe their conjunction. In other words, every time we see these two things together, we're learning not just about the base rates of those two things, but about their coexistence, about their covariation. And if we're successfully recovering all of that evidence, right, if we are an ideal observer who is picking up everything the world is putting down, let's say it takes 20 bits of observed evidence to make the association, then the prediction is that it's going to take about 85 pairings to earn the corresponding 20 bits of information about food versus red light, but it's going to take about 237 observed pairings to come to a similar conclusion about the association between the green light and the milk. Now again, this is all normative. The reality is different because we're not dealing with perception. We're not dealing with the possibility that there are other sources of information that the animal might be competing. But this is at least a way to design an experiment and ask, can the animal even learn this? Like how much easier or harder do I expect this to be? It's a starting point, and I think it's a really useful way for evaluating schedules. Now, I can anticipate what some of you might be thinking. I am unsure how to count all these states. That sounds like probability. I don't want to do calculus, and I have good news for you, because although that is a very common stumbling block, you actually don't need to do any calculus to get started with this kind of work. And it's absolutely fair that probability is confusing. We're not built for it, right? Everyone agrees that probability is counterintuitive. If someone tells you, I have perfect probabilistic intuitions, they're lying. We know this. Like, there's enormous amounts of research that people have bad probabilistic intuitions. Thank goodness the math can do it for us. So what my recommendation is to get started with this is simulation. You could, for example, as a first approximation, just break time in your schedule into 1-second chunks and just run the schedule with no animal in the chamber. You could literally even run a meta-associates box with no animal and have it record the state per second and count up how often are the various joint states available. In fact, that's actually a good way to debug your code and discover, hey, are things actually randomized the way they're supposed to be? Or have I left something on the table that the animal might be able to pick up on, some regularity I hadn't anticipated? Given a long enough run, proportions of joint events are going to converge on probabilities of joint events, right? It's still only going to be a sample estimate, but you can run this overnight, right? That's going to give you thousands of observations. Now, methods have been proposed to take this approach to much more complex schedules. That's beyond the scope of this talk, right? This can get as thorny as you like, but I think it's important to start simple if you want to get a taste for these sorts of tools. I also want to note that there's really no problem in using log base 2 or log base 10 or the natural log. They're just different currencies, but it's the same fundamental money, right? You can buy in dollars, you can buy in euros, you just have to convert between them. I'm going to relax. I've been working in bits because it's easy for our examples. I'm going to start to relax that going forward. Okay, so in practice, any statistical model that can describe its predictions as probability distributions, right? And that can be as simple as just a set of proportions. Any model can be subjected to this approach. If you can talk about proportions of events, you can do this. But again, that's the small world. Our models are sometimes wrong. They're sometimes very wrong. So another thing that we need to do is to ask how surprised one model would be by a second model. And to do this, I thought about, did I want to do some kind of sort of hypothetical experimental scenario? I thought, like, we need something a little more fun, so let's just go fully sci-fi with this. Humans are sending probes to another star to check out what we think might be a habitable planet, right? We're gonna go to the stars, finally, get out of this damn solar system. But the thing is, it's very far away. It's much too far to have even delayed computer control. We have to send probes to do the work for us and to send back the data. And we're going to have to give those probes some kind of a model of what to expect, because they're going to have to work totally autonomously. So we're going to keep things very simple for the sake of the example. We'll say, hey, we've got a sense that maybe this planet, this other solar system has maybe like kind of an Earth-like atmosphere. Let's assume it's like Earth. And if it's like Earth, then the probe's going to have a 29% chance of making a dry landing and a 71% chance of making a wet landing. We got to design our probes to be able to deal with water if they land on an Earth-like planet, right? Makes sense. This is maybe not the best model, but Earth is the planet we've got, so it's the model we can give the robots as something to work with. So we send them off into the universe, and crucially, we do need the probes to be ready for a dry landing, but when we don't get precisely the outcome we expect, we're going to have some kind of a surprise. So we're going to measure how hard a time, how much surprisal the probes are going to experience when they get the actual state of the world they encounter using what's called the Kullback-Leibler divergence. This can be thought of as pitting two different models against each other, the expected model versus the observed model. And this is also a relatively simple calculation. We take the proportion with which each small event x is observed, and we multiply that by the log of the ratio of observed events over expected events. So for every state of the world x out of a possible set of states big X, we're going to look at those log ratios. And if you think about it, this is also a kind of a weighted average, right? We're just saying, well, how often does the thing happen? Every time the thing happens, that's going to be contributing some share of the log ratio of these two events. The more surprised we are, the more discrepancy there is between expectation and observation, the larger this value is going to be. So, going into space, many years, our probe has traveled the light years, and what we have here is Planet Z, our alien world, at last. We've made it, or the probes have made it. Turns out it's a little different than we expected. It's actually only got 1% liquid water on the surface. It's more like Mars than it is like Earth, all told. So our robots are pretty surprised, because they were expecting they were probably going to have a wet landing. And if we run the math, then the Kullback-Leibler divergence of Planet Z given Earth is 1.692 bits. So a degree of surprisal that reflects that this is a very different planet from the one they were expecting. But here's the thing. We didn't really think to predict that Planet Z would be inhabited by hostile aliens. So the probes were completely unable to deal with this situation, and because we've upset these aliens, they are going to instead immediately invade our solar system, and they're going to make exactly the same mistake we did. They're going to predict what kind of assault robots to design for our planet based on their assumption of what their planet is like. So they build some robots, and those robots expect to have a dry landing, because of course, like, why would you prepare for a wet landing? It's a 1% chance. And the Kullback-Leibler divergence of Earth given Z is 3.853 bits. In other words, finding a planet with little water surface, our probes were pretty surprised. But when the aliens crashed in the ocean, they were very surprised. Now, there's a really important lesson here, and it's a lesson that took me a long time to fully internalize. Kullback-Leibler divergence is not a distance. Think about this. The divergence of Z given Earth is 1.69. The divergence of Earth given Z is 3.85. They're not symmetric. This is a really important point. Earth is a better model of planet Z than planet Z is a model of Earth. That's a state of affairs that we can run into. But like, once we step back and just like deal with the fact that those numbers are a little, maybe didn't comport with your assumptions, maybe it kind of makes sense because Earth's surface is more diverse. You are prepared for a wider range of circumstances if you ready yourself based on Earth's topography relative to planet Z's. And this difference falls quite naturally out of this particular detail. So if we zoom into this one element, and this is the ratio having to do with the water, since we don't experience rare events very often, they don't give us very many chances to reconsider our model. Rare events rarely teach us anything. But if we think something is going to be rare, and it's instead super common, we're definitely going to be surprised. We're going to, like, our average amount of surprise per observation is going to be way higher because we're going to have to confront that incorrect prediction about the world. So what does this mean in practice? Well, the Kullback-Leibler divergence renders in mathematical form something many of us actually have felt intuitively. When we see the impossible made possible, when we see something that we did not think was possible happen, it can be a shock, it can be overwhelming. And then, even just a couple years later, we might have a little difficulty remembering how surprising it was, right? We're now on the other side of that, and we're trying to convey to a student something, and we're a little surprised by how much their mind has been blown by that revelation. So surprisal here, as a general thing, as a general information theoretic quantity, reflects how much we should learn, but DKL reflects how much our model should change. How much do we need to update the model from its current state to the state that is being informed by the evidence that we've collected? Learning can be very slow when a subject is unaware that some outcome or relationship is even possible. If you've hand-shaped a rat, you know this. However, when events occur that are way outside of what we imagine possible, they can also be overwhelming. This has clinical significance. If you learn from those overwhelming experiences, if you form Pavlovian associations based on those overwhelming experiences, it can be much harder to go back. The distance you travel to get there is going to be very different from the distance it takes to return to your original assumptions. Okay. Now in the last bit of the talk here, I want to take a little bit of a detour, a little bit of a course correction. I want to think outside of just information theory as a thing we can measure. I want to think about what this says for the use of statistics in science generally. So let's consider that backbone of statistics. We know it and we love it, the negative log likelihood. In this formulation, we're saying that theta is going to be some model parameter about which we want to know more, about which we would like to collect evidence, and D here is going to be the data that we actually collect in order to educate our model. And the negative log likelihood is calculated simply by calculating the log of the conditional probability of the data conditioned on those parameters, and we can take the negative sum of those observations, or the integral if we're working with continuous distributions. The value of theta that minimizes the negative log likelihood is the maximum likelihood estimate. So in classical statistics, when you're fitting a curve, minimize the negative log likelihood is the same as maximizing the likelihood. hope that's obvious, because the sign, we had to flip the sign, right? So that's going to be more working minimums rather than maximums. But note the similarity to Shannon entropy, right? We've got a log probability, and we're looking at some proportion of it. In the negative log likelihood, we just have the sum of some probability. All that's missing is dividing by n. There is a fundamental connection between information theory and the basic notion of the likelihood in classical statistics. And this is not accidental, this actually features in many of the core proofs in these areas. And this brings us to something that was actually introduced introduced very nicely by Dr. France. It was mentioned in a number of other talks, which is this idea of information criteria. So this link between likelihoods and entropy is the foundation of this tool. Information criteria are a whole host of tools for model selection that allow us to basically say, hey, which of these models is doing a better job at describing the data I've got? So suppose you collected some data D for describing the behavior, and say you have multiple competing models. They might be different discounting curves, right? We might want to compare RAC versus RAC2, however we want to, whichever things we want to pit against each other. And you'd like to see how well those models do when you fit the parameters for theta, when you find the parameters that are your best fitting parameters. You might have other predictors you need to feed in as well, right? If it's, for example, something like a regression model, you might need to feed in the predictors. If it's discounting, you might need to feed in time and so forth. Now, how do you define doing well? Well, we already know, right? We basically don't like being surprised. If we're dealing in information theory, surprisal is the thing that we're trying to minimize. And that's exactly what we need for this purpose. When a model makes good predictions, then every new case X from our data set will have low surprisal compared to our prediction if it's a good model, right? We might not always hit the bullseye, but we're not going to be way off from the bullseye all the time. If we consistently make small errors, we're going to experience correspondingly little surprisal. Poor models fumble more often, and they fumble to more extreme degrees. So those are going to be harder to predict. They're going to engender larger levels of surprisal. So a popular way of framing whether or not a model is doing well is whether or not it makes accurate out-of-sample predictions. Whether you can predict a state of affairs you have not measured yet, and then when you measure it, get at least close to the right answer. The more accurate those out-of-sample predictions, the better the model by this logic. And this brings us to the original OG information criterion, the Akaike information criterion. This is the oldest and the simplest criterion, and for those of you who've encountered it before, which I suspect many of you have, it has a blessedly simple formula. All we have to do is to take the negative log likelihood for a particular model. We add k, which is going to be the number of free parameters, and we multiply that whole thing by 2. That's then going to give us a score, and whichever model gets the lowest score felt the least surprised, experienced the lowest degree of average surprisal per data point. Now, given that we have some different set of models, we're minimizing surprisal. I do want to make some very small technical notes because I want to make sure not to offend any actual statisticians who might be creeping in the shadows with a knife. First of all, we have to use the natural log for this for reasons I don't want to get into, but it's not technically AIC if you're using different units. What the correction k here is doing is it's correcting for overfitting, because when you calculate this, you don't actually get to view out-of-sample data, right? You're not going to run the experiment a second time. The whole point of information criteria is to not have to do that, but we know that models with more parameters tend to get overfit, and there is a rigorous, motivated reason why adding a constant that is equal to the number of free parameters corrects for that. The times 2 that's there is there because the chi-square distribution is used in the derivation. So like, it's there for a good reason, but you would get the same minimum if you didn't include it. I encourage you to actually include it because it's there for a reason, but it's not a reason most of us have to engage with. So what does this have to do with Kullback-Leibler divergence? Now, there is a magic trick that I want to convey to you that Akaike sussed out. Because here's the thing, we never know the true state of the world. I'm going to call it Model Aleph. Shout out to any fans of Borges in the audience. Model LF is the model that is the actual random generating process for the world that we do not have access to. If only we knew that reality, if only we knew what the real generating process was, the true model of the world, then we could trivially use the Kullback-Leibler divergence to see how far off each of our models is from it and pick which one was better. So we could just calculate the mean Kullback-Leibler, basically the mean log ratio for model LF given model 1. And we could also do that for model LF given model 2, right? And then that would tell us at least how far off our theoretical models are, if we could sort of see the mind of the LF. I'm going to do a little arithmetic here, because after all, the log of a ratio is just the difference of the logs. And I can take the mean of the difference and split that into the difference of the means, right? This is all legal. And this implies something bananas. That is that the difference between those two divergences is equal to a quantity where model LF seems to have been factored out altogether. I really want you to dwell on what a ridiculous magic trick this is. This implies that we can compute whether MLF diverges more from model 1 than from model 2 without knowing model LF. That's ridiculous. Now, it is of course more complicated than that, and that's why there's that correction for overfitting. Because in practice, to actually know what the average of the log probability was, we do need to know what the true base rates of events are, and our model has probably overfit somewhat in making those predictions. But this is the basic notion, right? This is the magic trick where we somehow factor out the unknowable mind of God and get the right answers to which of our models is probably the better model. It's magic. So since its development, there are other information criteria that have been developed that have better long-term properties. The most common of these that I've seen in the literature is AICC. There's really no reason not to use it because for large samples it converges on AIC, and for small samples it's more robust. It deals with edge cases better. So if you're going to use AIC, you should probably use AICC instead. A more recent development is CAIC, and that puts a greater emphasis on parsimony than on prediction. It tries to sort of split the difference between making good predictions out of sample and choosing parsimonious models with fewer parameters. And finally, we had a brief mention yesterday of WAIC, which is a very powerful but more technical generalization of this strategy that allows you to bring in things like regularization and non-normal posterior parameter distributions that can be very powerful with regards to multi-level models, nonlinear models, etc. So to quickly summarize what I've guided you through here, entropy is at once a measure of disorder. That's the way we usually hear about it in pop culture, but it's also a measure of surprisal. And as scientists, its characteristic as a measure of surprisal is actually a lot more compelling because we're trying to predict the future state of the world. It measures how little you know about your next observation, but also how much you learn from observing it. And that's useful if you want to think about the information organisms are potentially taking from schedules. Association could be conceived, at least at a normative level, as conditioning or predictions on the data that you've already observed, on the relationships about the world that you are already confident in. And therefore, mutual information is a really useful normative measure to at least get a sense of your schedules. It's not going to predict all your experiments. This is not a panacea, because again, all the models we're working with are wrong to begin with, right? So there is no free lunch, but this is useful for thinking about, can the animals learn this? Is this schedule harder than that schedule, at least to a first approximation? Now, information theory also provides powerful tools for characterizing the discrepancy between prediction and observation. I gave you the most basic of these divergence metrics, which is the Kullback-Leibler divergence, and this provides the motivation for a whole host of really powerful information criteria that are really a must-have in the modern scientific arsenal. Now, you may notice there have been some superscripts throughout the talk. I have, in fact, provided a complete reference list for all of the things I've been quietly citing during the talk. These go into much more depth than what I can cover in this talk, or indeed what Ryan, myself, and Peter Balsam were able to co-author in a little review of this paper that is my second citation there. But these are all very much worth your time. With that in mind, I want to thank you all for coming and for your kind attention.